now the talk of Professor Dani, Lattice subgroup actions and determining approximation is indirect quadratic form.
Say, yeah, and then what linear form. And we want to look at its values on the set of integers, and we want to know when is it dense. Dense in R. Now, all of you know that the answer is that you cannot give L is not proportional to a rational form. Everyone would have his favorite proof of this, and we'll not talk about that. The next thing, usually in this line, people start talking about quadratic forms, and then go to Oppenheim conjecture and so on. But I just want to look at, next consider let f equal to L1 times L2, L1 and L2 linear forms. When we ask the same question, when is f of Zn dense in R? Now, of course, I have already mentioned quadratic forms, and this is a quadratic form, and then Oppenheim conjecture comes to your mind, and then suddenly you realize that it won't work because this is no longer is not non-degenerate. I mean, either if n is at least 3, the form is degenerate. It's already a product of two linear forms. So so f is either degenerate or n equals 2. In either case, you don't have the Oppenheim thing. Nevertheless, it turns out that it's true that I don't know whether I should call it a theorem or f equal to L1, L2, L1, L2 linear forms. Linear forms on Rn. Now let me take n bigger than 3. Then f of Zn is dense in R. At least one L1 and L2. L2 is not proportional to the rational form. Now,
I'm sorry. This.
Yeah, I'm going to say that. I hope the statement is clear. There's some complaint that the handwriting is small. I'll try to improve upon it, but I hope this statement is clear. Okay, this theorem I would say is now an exercise, but if you are not inclined to spend time on doing the exercise, it is included in one of my papers. I don't know the reference, but I can provide it later. And it depends on the following. and this is my theorem with Raghul. So if you have let L1, L2, Lk be k linear forms on Rn and greater than k, and you want to look at then if you look at values of L1V, L2V, LKV. Now this is in Rk, R power k. So let me look at this set of values being Rn.
All values, not integer values.
Oh. And take the closure of this. One can precisely describe the closure in terms of, see if before I write what it is, notice that if sigma lambda I Li is rational or an integral form is an integral linear form, then sigma lambda I Li V, this is going to be an integer. So look at and the Massett condition is statement is precisely that these are the only constraints. So to write it down scientifically, what I will do is that is precisely the set of V1, V2, Vk such that sigma lambda I Vi is in Zn whenever sigma lambda I Li is an integral form. So you can get, and in particular, so this is dense in Rn power in R power k, if and only if there is no linear combination of the Li's with making it into a rational. So that's generalization of what we started with, and now knowing this, one can reduce this. It's obvious. For instance, if it's okay, I don't think I will spend time on that. It can be reduced from that, and has been explicitly done. Now we are still left with the condition that n is at least 3, and the rest of the talk is going to be about n equal to 2. What happens in n equal to 2? And at this point, let me mention that most of what I'm going to say after this is joint work with Noguera.
Can I ask, I'm sorry, I think I'm a little confused. So L1 of V through Lk of V are real numbers. And then on the right side, you have a subset, it looks like of Rn to the k. Right, so this is a subset of
Yeah.
R to the k. And then your little VIs are vectors, or are they numbers? I mean, just numbers. So then I don't know what it means, summation lambda VI is in, it's in Z or it's in?
Yeah, please.
Should be Z, not
Z, not Z
yeah,
to Z.
it's-
That's right.
Just erase the N.
And
That's
yeah. Okay. Yeah. See, I explained the constraint, and you can write the. I suppose. Yeah. So now we are interested in products of two linear forms in n equal to 2, and after some simplification, I can just write as x minus alpha y, x minus beta y with alpha beta in R. Because this is this also gives you up to some scalars wherever this also gives you any indefinite non-degenerate form in n equal to 2. So that is the most general thing that you can ask. We need to clarify at this point. So x y equal to this. Now we all know that the analog of the Oppenheim conjecture doesn't hold for n equal to 2, and so we know that Q of Z2 is not dense in general. Not dense in general. Maybe good to recall some cases or issues that are involved. The first thing is, if alpha and beta are two conjugate quadratic numbers, then you see that this form, even though written as if alpha and beta are conjugate quadratic numbers, then QZ2 consists only of integers, right? So it's not dense. Secondly, a somewhat larger class of counterexamples arise from what are called badly approximable numbers. So if alpha and beta are badly approximable, then there exists delta greater than 0 such that Q of Z2 closure avoids the 0 delta except for the mandatory 0. So if I take two badly approximable numbers, let me quickly recall the definition of badly approximable numbers. You will see. So recall the definition. Theta in R is said to be badly approximable if there exists, if we can use this number delta such that theta minus p by q is greater than delta by q squared for all p q integers, q not equal to 0. And this you can write variously as qp minus q theta minus p is greater than delta by q, and using that you can see that a neighborhood will be avoided. Okay. For all. Well, here in this case, though I would go to that. You can also take one of them badly approximable and the other is 0. One of them 0 will also work, but the typical thing I want to look at here is both being badly approximable tells you that a certain neighborhood of 0 is avoided. Now we are going to relate this to Dani approximation properties, and the thing that one sees, the sort of connection with Dani approximation, is that now recall a continuous fraction expansion and what it tells us about fraction expansion. So, in a given, starting with any real number, we have a way of writing it as a continuous fraction expansion, 1 over a2 plus etc. I will not elaborate on this. I think everybody knows that this can be done with a naught and integer and ai are positive integers or natural numbers. Now, since I am going to read this, let me say that remark there is a 1-1 correspondence between irrational numbers. If I take all irrational numbers and sequences a n with a 0 in z and a n in n via a continuous fraction via continuous fraction expansion. For every irrational number, you have such an infinite expansion, and conversely, if you are given such a sequence, there is always an irrational number to which it corresponds. Coming back to these properties, so proposition number theta in R is quadratic if and only if I am going to write this as the corresponding continuous fraction expansion is eventually periodic, which means that if you write it down as a sequence, then after some stage you will see the same block repeating. And secondly, theta is badly approximable if and only if ANs are bounded. So we sort of see that these two behaviors correspond in terms of Dani approximation to the specific cases where it's either periodic or the weaker condition that they form a bounded sequence. Now we asked a question: can we say something about when the values are going to be dense? And here is the answer. So for that, let me define a term for you. Theta in R is said to be generic if every block of positive integers occurs in AN. What does it mean? It means that that is given B1, B2, BL for whatever L, BI positive integers, there exists we say N such that AN equals B1, AN plus 1 equals B2, etc. To cover all of them. So if if every block occurs in the sequence AN, then we call it generic. Notice that if every block has to occur, it has also to occur infinitely often, because you can always think of it as a part of a bigger block, and since the bigger block has to appear, so the block you have must occur infinitely many times. Every time you can produce a new one. Okay, and here is a theorem. If at least one of alpha and beta is generic, then Q of Z2 is dense in phi. Now, this is actually a consequence of a very old theorem due to Emil Artin. So, consequence of Artin's theorem, and let me write down what is Artin's theorem. Before that, let me get down to some notation. It's going to be about geodesic flow on surfaces of constant negative curvature. So you have the model of the upper half plane, and you know that all geodesics are given by 2 points alpha and beta. So this for each geodesic path, you can associate a pair of points. We are now going to do the other way. Given the pair of points, I'm going to think of this geodesic, and Artin's theorem tells you that let me call this as the G alpha beta as my geodesic running that, and let G bar alpha beta, G bar alpha beta, the projection on the modular surface. I should say by G. Okay, let me. G alpha beta be the geodesic orbit in the unit time invariant corresponding to alpha beta. By this I mean, along with the path, you always associate with the unit time direction. And G bar alpha beta, the projection of the modular surface on H modulo essentially. Can you bring to your memory the usual picture of the modular surface? I am projecting on this, and now the theorem is that G bar alpha beta is dense in the unit time invariant H, if and only if one of at least one of alpha beta is generic. Now, the fact that it sort of just depends on at least one is that these paths are dense if and only if either the positive side or the negative side are dense. So, let me now put this in a slightly different perspective, more with homogeneous spaces. So the thing that I'm going to look at is P cross P Okay, this is the P, where P is the projective space, one-dimensional projective space, and consider the action of let me also say G equal to SL2R. Consider G action on P cross P. Okay, so now this is what? This is the G action has exactly two orbits, the diagonal and off diagonal. So the P cross P minus delta is a G orbit, and the stabilizer of let me take the point E1 bar, E2 bar is the standard basis, is exactly D equal to lambda 0 to mu on the diagonal matrices, right? So the only matrices which these two lines invariant are given by that. So therefore, this space is stabilizer is D. Sorry. The group of diagonal matrices. So this space is G modulo D, and I'm sort of going to ignore the extra connected component and think of this as the geodesic flow. And what we are looking at is we want to look at SL2R action, and in fact I want to restrict it to SL2Z Z actions. So let me call gamma equal to SL2Z. So here you have gamma acting on this, and you would ask what are the on the one hand, one would like to understand the orbit structure of the gamma action, and that there is a clear duality between the gamma action on G modulo this subgroup and the action of this on G mod gamma. So this gamma acting on that, and you can take G mod gamma and act by the geodesic flow. This action. There is obvious duality. In both cases, the orbits are given by this, right? And so this is what brings the relation between Artin's theorem and the result that I mentioned. So here now you can think of, in the projective space, you think of the cosets corresponding, the represent the sort of classes lines with these as the lines, then the theorem then corresponds to gamma orbit is, so yeah, when you want to think of gamma orbit of, we are reduced to looking at gamma orbits of, there is an extra point at infinity which I'll ignore, and so I want to look at orbits of these. And this orbit structure is understood in terms of the diophantine conditions that I told you about. And The actual conditions to write down about orbit closures will turn out to be a little complicated. Right? I will not do that. I mean, because I want to go over something more now after this. So, but there's a relationship between the considering the gamma action on not just P but P cross P. Instead of, rather than thinking of this space, let me now think of G mod P1 cross P1 and or rather the points. I mean, I'll stick to the copy of the real line in this and a copy of the real line in this, and then we understand we can consider the gamma orbits, and yeah. So then via that one can translate the Artin's criterion for the density of this orbit to the condition that I mentioned. Namely, if at least one of them, one of alpha and beta is generic, then this gamma orbit is fixed. Now, so another
in Lattice theorem, you made if and if and only statement.
Yeah, the consequence is not we don't exactly know, but yeah. Okay, so Arnaldo and I looked at the question just as the action of gamma acting on P cross P, and not only that, we then also considered this orbits not of the whole of gamma, but you can take gamma plus acting on P cross P. And this we analyzed using the Euclidean algorithm and things like that, and found got certain information about the orbits, which doesn't turn out to be as neat as to spend time on that. But let me give a consequence of this. So
What's gamma plus?
Where gamma plus equals A, B, C, D. This is first of all in G and in SL to Z, in gamma and A, B, C, D positive. Yeah. ABCD. It's a semigroup. And one can talk of orbits of the semigroup under the action. And though I will not go into the description of the orbit structure or information on orbit closures, one consequence of it is that the Q of n cross n, I should get back, let Q equal xy equal to x minus alpha y, x minus beta y, if alpha is, say this one, or beta is positive and generic, then Q of N2 is dense. So not only on all integer pairs, but positive integer pairs is actually dense. And if you want this conclusion, it is in fact indeed necessary that you assume this positivity. And from this you can of course get back to the original. Now I hope I have spent how much time I know. Okay. So the second thing I want to talk about is the analogous question for complex numbers. Complex quadratic form. Let me recall for the audience that in this case the analog of open-end conjecture holds, and this was proved by Maharaja and Vadodara. So we know that if Q is an indefinite non-degenerate, if indefinite is automatic, Q is a non-degenerate quadratic form on the n because of 3 not proportional to a rational form, then now in place of the integers, I'm going to take Gaussian integers. Q of the n is dense in C. Here G is equal to Gaussian integers, that is x plus iy, xy integers.
And rational is also with respect to this speed, right?
Pardon?
Rational is also with respect to this speed.
Yeah, but I suppose that's a more well-known terminology. So if you have so rational means both x and y are rational in the usual sense, and okay. So
Not proportional to rational form. That rational is in what sense?
pardon? Yeah, the coefficients are rational in this complex. A complex number is rational if both real and imaginary coordinates are rational, and the form is rational if all the coefficients are rational complex numbers. And now, and similarly, in the way I said, I think product of two linear forms will also have the analogy property that I mentioned. Though this is it should be an exercise. And yeah, so now again, like we would like to think of n equal to 2 case primary quadratic forms. So let's write down Q of ZW equal to Z minus alpha W, Z minus delta W. Okay, so you notice that we used quite a bit of continuum fractions for real numbers. Now in the case of complex numbers, the kind of interrelationship between continuum fractions and is analogous theory has not quite developed as much as in the real case. So we have to sort of set out building up some analogous things, and part of what I'm going to talk about is concerns that part of the theory. So first of all, continued fractions. Fractions for complex numbers. Let's have this explained, and we have some numbers right here, and there are 4. These are Gaussian integers that you find near them. A naive thing one might think of is to take the real so starting with say theta, complex number, you want to write it as because you want to take out some an integer, and for the first candidate you might think of in analogy with the real case the integer parts of real and imaginary components. But there is a problem with that. You cannot really do it because not everything in this square is within distance 1. So if you just decide to take out this part, you will end up with something that which is not less than 1 in absolute value. Okay, so let me call this, say, A naught. It need not be this, but then you could agree to take one of these other points, points in the Gaussian integer, or one of these other Gaussian integers as A naught. Let's say we have done that, so then you are left with something which is less than 1 in absolute value, and then you can think of proceeding with in this. One particular way of doing this that was analyzed quite long time back by Hurwitz in the 1880s is the Hurwitz algorithm, and that is simply to say that you pick the integer that is nearest to the number that you have. Okay, this is here, this is the nearest, you pick up this for the nearest one. Then you have the next one which is less than 1, so when you invert this number is here, the number here is greater than 1 in absolute value. So you proceed in the same way, take the nearest Gaussian integer for A1 and so on. Okay, so now here you need to be able to conclude that this would actually converge. It's not automatic. I mean, in the usual continuum fractions you had it ready-made, but now Hurwitz proved that proved a few things which I recall. That so let's write down PA. We have 1 over AN.
There could be more than what nearest number that you choose.
Yeah, we will not bother about that. You choose by something. So this up to n, the rational number that you get, let's call it Pn by Qn, and Hurwitz proved that Pn by Qn in fact converge to Z, and also proved the analogs of some of the things that I mentioned. Z, quadratic. Now here, this is in terms of Gaussian integers, I will not write down. Z is quadratic if and only if the ANs are eventually periodic. Okay, but there are, while I mean this is a certain extension of the continuum fraction expansion idea to the complex case, there are several drawbacks to this. Firstly, it no longer has the same kind of relation with that. I mean the approximability, etc. In the complex case. So from a number theoretic point of view, it is quite different from the usual continuum fraction expansion. It doesn't have that level at all. And that has been addressed by some papers of Loeck in terms of classical number theory by looking at algorithms which do not tell you what to do, which at the nth stage depend not only in that particular integer but something of the entire past. So what we call non-Markovian algorithms. But that's not the direction I want to go into. The second drawback from my point or perception is that recall that I emphasized that in the classical case is an exact one-to-one correspondence between the sequences and the rational numbers. So if I am given a sequence, I can always get back an irrational number. And here, it turns out that you can no longer do that. In fact, we don't know any natural description of all the sequences, any way of expressing all these sequences that come from the Hurwitz algorithm. So, in particular, it's not even a subshift of, I mean, you cannot even exclude certain finitely many blocks, etc. So it turns out there are arbitrarily long restrictions. So on the end, the entries there are restrictions in the entries, and they will involve longer and longer strings. I'm sure this is vague, but I will not go more into that. One would like something where, of course, you do not in general expect that all sequences should be capable of giving a complex number, but at least under some conditions you should be able to say that. And that is one of the things that we have addressed. And here is the theorem. Okay, so I'm no longer thinking of this one as the. So let me start again. So I start with Z now. Write A naught in whatever, picking whatever is admissible. So take. Think of writing such sequences irrespective of algorithms. You given any Z, you pick one of the integers that is within distance 1, take that, and the remaining part you have some Z1. Take A1, which is any Gaussian integer within distance 1, and so on. You can write these sequences. So now the only main question is whether you start with sequences, under what conditions can you be able to say that it actually does represent a complex number. Okay, so now theorem. Okay, first of all I'm going to assume let n be a sequence of Gaussian integers, sequence in G. Let's suppose that I'm going to suppose this is kind of mod n is greater than 1 for this for all n bigger than or equal to 1. So look at the Gaussian integers. We have 1 minus 1 minus I. Here we have 1 plus I, and so on. There's 2 here. Now we are going to avoid all of these, exclude all of these, and it is still possible to, they are not really needed for the expansion. Now the conditions, I am going to put further conditions on the occurrence of these 8 entries here. 4 from this square and 4 from the next takered square, and that is the following. If mod an and if if mod an equal to root 2 or mod an plus 1 equals root 2, which means one of these 4, then an plus 1 bar is greater than 2. Greater than or equal to 2. So notice that you can explicitly write down what the pairs are, what the convenient way of writing turns out to be in terms of this inequality. It excludes certain number of pairs from the 16 pairs that you have, and another analogous condition involving another similar condition involving the next square as well. If an is mod an is less than or equal to 2, and here is and mod an plus 1 is less than or equal to 2, then either real part of an plus 1 is bigger than or equal to 0, or imaginary part of an plus 1 is equal to plus or minus 4. Now on the actual conditions, you can see that the conditions only involve these 8 integers, and only some of the pairs have been excluded. Okay, then A1 plus 1 over A1 plus etc. represents a complex number. In the obvious sense that if you take the truncated sequences, they converge to a complex number. Conversely, every complex number, every irrational complex number admits representation as A0 plus 1 over A1, etc. So to speak, in terms of symbolic coding, this gives a more satisfactory situation where you can pair numbers. There's no uniqueness of pairing. Of course, you do not expect that, because you saw that there was a certain degree of arbitrariness about flexibility in the way you could choose the Gaussian integer. But this gives a sequence with a class of sequences which can be nicely related to the expansions. So this would, in particular, enable you to define generic elements. So you could take, now you have certain sequence of space of sequences, and you can define genericity if the block condition of exclusion is satisfied. Any block which satisfies the condition of specifically excluded can do not. No. So one possible way of make this is may use definition. So you can call a generic if any block satisfying conditions 1, 2, 3 occurs in A. Now, this definition I think would be a good definition, but and the set of sequences which fulfill that would actually be a dense G delta set. However, there's some difficulty in proving the measure to be full measure. We have not quite succeeded in showing that it's a full measure. That's something that remains to be understood. So we then went to a modified definition, for which actually it would be okay to use the Hurwitz algorithm itself. So generic for Hurwitz algorithm is not satisfactory, but something that we can manage. Namely, so let An be a Hurwitz expansion. Of Z. To call it generic, call Z generic if blocks B1, B2, BL which is admissive, which occurs in some expansion occurs in A. It's I suppose you understand what that means. Actually, we also this slightly weaker condition is possible here. We know that certain blocks are excluded, but given any block, ask yourself if that there are complex numbers for which it appears does occur in the differential, and then you expect that in that case it should occur in the expansion that we are looking at. So this sort of has its own problems, but nevertheless one knows that the set of
How many doing?
pardon?
How many minutes doing?
How much? 5 minutes? Oh yeah. Okay. I'm sorry.
4 and a half.
Pardon?
4.5.
4.5. Well, allowance for erasing this board. Okay, so yeah, I'm at the end anyway. So now the thing that I want to say, I defined generic with respect to, so let's say G, generic numbers for Hurwitz algorithm. Then G is dense G delta. And one also knows in this case that the measure of is equal to 0. And this is a consequence, is not something we proved, but it's a consequence of follows from theorem of the NC. So like the Gauss map for the usual continued fractions, you can write the Gauss map for the nearest for the Hurwitz algorithm, and that map, the Gauss map, is studied by Hensley, who showed that it has an invariant measure, invariant probability measure, with respect to which it is mixing. And then with that, we conclude that the set of generic points will in fact have full measure. Okay, so the final thing is just another of what I said before. Z minus alpha W, Z minus delta W, if at least one of alpha delta is generic, then Q of G2 is density. Yeah, thank you.
In your some theory, you use the notion of generic numbers, yes? I think sometimes you can change generic for better approximation. Or there exist counterexamples.
No, these are not like Van they're more like
But it's approximately, of course, more.
no, and it's
So this is just one direction, right? Generic implies dense, and we don't know if it's a phenomenon. The other question is, does this Gauss map can you relate it to the geodesic flow on SL on H3 mod the Bianchi group?
the
Or
relation
H3 mod SL2 0
I said 2C modulo
Yeah, Picard, sorry, not Bianchi. Sorry.
I said 2C modulo SL2G would yeah, I mean, and then the diagonal flow, it will be related to that.
Okay. Okay, so
Section. What is the section?
probably the natural extension of the gas map should be a 4 gray section of the
Yeah.
frame.
Yeah.